3, 2, 1. MDS, we have ignition, we have a liftoff.
There is a machine sitting on a launch pad in Florida. It weighs less than a family car. It runs on less electricity than a light bulb. And it is about to leave the world that made it, forever. No one watching the launch fully understands what they are witnessing. They see a rocket. They see fire and noise and a trail of white smoke curling against the blue Florida sky. What they cannot see is the deeper truth beneath the spectacle, that this small machine, fragile and improbable, is going to outlast almost everything. September 5th, 1977, Voyager 1 lifts off from Cape Canaveral aboard a Titan III rocket. The launch window is narrow, chosen with great precision. A rare alignment of the outer planets, one that occurs only once every 176 years, makes it possible for a single spacecraft to use the gravity of each world it visits to fling itself toward the next. Without this alignment, the mission as designed would be impossible. The engineers and scientists who shaped it understood they were building something for a moment that would not come again in their lifetimes. The spacecraft itself is compact, a 10-sided aluminum frame with booms extending outward, carrying instruments like limbs. Its primary antenna, a large dish more than 3.5 meters across, points back toward Earth. It always will. Attached to its body is something that has nothing to do with planetary science. A 12-inch gold-plated copper disc. On it, music from a dozen cultures, greetings spoken in 55 languages, the sound of rain and surf, and a mother's first words to her child. Mathematical diagrams that explain where Earth sits among the stars. Instructions for how to play it, encoded in the metal itself. It is a message in a bottle, dropped into an ocean with no shore. The engineers who built Voyager gave her instruments to see. They gave her a record to speak, and then they aimed her at the outer dark and let her go. 16 months after launch, the black between worlds gives way to something enormous. Jupiter fills Voyager's cameras slowly at first, a pale smear growing over weeks into a banded, turbulent giant. By the time Voyager makes its closest approach in March of 1979, the images coming back to Earth are unlike anything ever captured. This is not the calm, distant point of light astronomers have watched for centuries. This is a world in constant, violent motion. The cloud belts churn. Wind speeds measured by tracking cloud features exceed 500 meters per second in places. The Great Red Spot, a storm system that has persisted for centuries, sits embedded in the southern hemisphere like a wound, wide enough that the entire Earth could fit inside it with room to spare. Below those cloud tops, lightning discharges flash continuously. Not the thin, forked kind familiar from Earth, but enormous superbolts with energy millions of times greater. But Jupiter itself is only half the story. As Voyager swings through the Jovian system, its cameras turn toward the moons. Io, the innermost of Jupiter's large moons, was expected to be a cold, cratered world not unlike our own. What the images show instead stops scientists in their tracks. Umbrella-shaped plumes rising from the surface. Active volcanoes. Io is the most geologically active body in the solar system, squeezed and heated by the gravitational pull of Jupiter and the other moons until its interior stays molten. Some eruptions paint the surface in sulfur yellows and reds. The landscape changes week to week. Europa reveals a different kind of promise. Its surface is bright, unusually, almost uncomfortably smooth. Dark reddish lines cut across it in overlapping networks that look nothing like meteor impacts or volcanic activity. They look like cracks, like something beneath the ice is moving, pressing upward, refreezing. The implication, debated quietly in 1979, but growing louder over the following decades, is that under that ice there may be liquid water, an ocean, sealed in cold and darkness, far from the warmth of the sun. Ganymede shows a surface of two ages, ancient dark terrain preserved from early impacts alongside younger grooved regions where the ice has shifted and reset. Callisto appears to have barely changed in 4 billion years, its surface recording every collision since the early solar system like a ledger of catastrophe. Then Jupiter does something for Voyager that no rocket could. It gives her speed. As the spacecraft swings behind the planet, Jupiter's immense gravity transfers a fraction of its own orbital momentum into the trajectory of the small machine. Voyager 1 exits the encounter faster than she arrived, now aimed at Saturn on a path no fuel alone could have purchased. The planet gives what physics allows. Voyager takes it and moves on. Saturn arrives in November of 1980. From a distance, the rings look solid. A flat disk of light encircling the pale beige planet, clean and geometric, like something drawn with a compass. Up close, Voyager's cameras tell a different story. The ring system is not a disk. It is thousands of individual ringlets, each one a stream of particles, water ice mostly, ranging from grains to house-sized boulders, all orbiting in their own precise paths. Between the rings are gaps. Within the rings are waves, braids and edges, maintained by the gravitational influence of small moons embedded in the system. Some of those moons are sculptors. Prometheus and Pandora flank the narrow F-ring, and their gravitational tugging keeps it confined. Pan sweeps its own lane clean. Mimas creates the Cassini division, a wide gap between the A and B rings, through orbital resonance, the mathematics of gravity written visibly in ice and rock. Saturn's magnetic field is smaller than Jupiter's, but still enormous compared to Earth's. Voyager's instruments map its extent, measuring the energetic particles it traps and the way the solar wind compresses it on the sunward side while stretching it back on the night side. The moons are diverse. Mimas carries an impact crater so large relative to its size that whatever struck it came close to shattering the entire body. Enceladus is surprisingly bright, so bright it reflects nearly all the sunlight that reaches it, a sign of a young, active surface. Each one is its own world in miniature, shaped by forces unique to its history. But Titan is why Voyager bent her path towards Saturn the way she did. Titan is the largest of Saturn's moons, larger than the planet Mercury, and it alone among all the moons in the solar system possesses a thick, permanent atmosphere. From orbit, Titan is featureless, wrapped in an orange-brown haze so dense that Voyager's cameras cannot see the surface beneath it. What the instruments can measure is the atmosphere itself, nitrogen-dominated, much like Earth's, laced with methane, with complex organic molecules forming in the upper layers as ultraviolet radiation breaks apart simpler compounds, and the pieces recombine into something heavier, stranger. The surface pressure on Titan is about 1.5 times what a person would feel standing at sea level on Earth. The temperature is not. At -179 degrees Celsius, methane can exist as a liquid. It might rain, it might pool. There may be rivers and lakes and deltas on Titan, carved not by water, but by liquid methane trickling over a bedrock of water ice. It is not life, but it is chemistry. And chemistry, given time and energy, has a way of becoming interesting. The close passage of Titan curves Voyager's trajectory permanently upward out of the plane of the solar system. There will be no more planets. The gravity assist at Saturn is the last one physics offers. From here, Voyager 1 is on her own heading. 13 years after launch, someone has an idea. The spacecraft is now nearly 6 billion kilometers from Earth. Her cameras have been pointed outward since Saturn. Trained on whatever lies ahead, they are no longer needed for planetary science. Soon they will be shut down permanently to conserve power for the instruments that still have work to do. But before that happens, the scientist who proposed the mission, Carl Sagan, asks that the cameras be turned back toward home, back toward the inner solar system and the pale warmth of a distant sun. It takes months to get the geometry right and to protect the cameras from accidental exposure to sunlight. But in February of 1990, Voyager 1 pivots. She takes 60 frames across the solar system, a mosaic portrait of the neighborhood she left behind. In one of those frames, barely visible against the scattered light of the camera lens, is a point of brightness smaller than a single pixel. It is Earth. Every person who ever lived, every war ever fought, every act of love and cruelty, every dream, every discovery, every prayer aimed at a sky that never answered. all of it contained in a dot of light so small it could be mistaken for a piece of dust on the lens. Sagan spoke about that image in a way that lodged in the mind. He described it as a mote of dust suspended in a sunbeam, not as comfort exactly, but as perspective, a reminder that the rivalries and certainties that fill our days happen on a world that, from a sufficient distance, cannot be seen at all. After the portrait is finished, Voyager's cameras are powered down for the last time. She stops looking back. She continues forward, and the numbers on the odometer keep climbing. For 35 years after Saturn, Voyager travels without a destination. The heliosphere, the vast bubble of solar wind inflating outward from the sun, has edges. The solar wind, a constant stream of charged particles blown outward from the sun's corona, eventually meets the resistance of the interstellar medium. The region where the pressure of the wind equals the pressure of the space between stars is called the heliopause. It is not a wall. There is no line painted across the void. But there is a measurable transition. Voyager's instruments, some of them still functioning after 3.5 decades, are watching for it. What they detect is a shift in populations. The energetic particles that originate from within the heliosphere, carried outward by the solar wind, begin to drop sharply in number. And particles that originate from outside, cosmic rays produced by distant supernova and other violent events across the galaxy, begin rising just as sharply. The magnetic field orientation changes. The environment is different here. On August 25, 2012, after 35 years of travel, Voyager 1 crosses the heliopause. She becomes the first human-made object to enter interstellar space, the space between stars, a region that, for all of human history, has existed only as a concept, unreachable, theoretical. Now, something humanity built is inside it, measuring it, sending data home at the speed of light across a distance that takes those signals more than 17 hours to cross. The data comes back faint. The transmitters on Voyager produce about 20 watts of power, comparable to a dim refrigerator light. By the time that signal crosses the void and reaches the enormous antennas of NASA's deep space network on Earth, it has spread across billions of kilometers of space. What arrives is nearly nothing, a whisper, detected only because the antennas are very large and the engineers who built the ground systems understood how to listen for something almost inaudible. But it is there, it arrives, and it is read. The power is running out. Voyager 1 is kept alive by 3 radioisotope thermoelectric generators. They work by converting the heat produced by the natural radioactive decay of plutonium-238 into electricity. At launch, they produced roughly 470 watts. Every year since, the output has declined by a small fraction as the plutonium slowly exhausts its half-life. By the mid-2020s, the available power is down to a fraction of what it once was. One by one, instruments are turned off, not because they have failed, but because there is no longer enough electricity to run them all. Each shutdown is a calculation, what can still be learned versus what it costs to keep a system powered. The teams that make those decisions are working with instruments built before many of them were born, maintained by documentation handed down through generations of engineers who themselves learned from the generation before. There will come a moment, expected sometime in the late 2020s or early 2030s, when the power level drops below the threshold needed to operate any science instrument reliably. After that, Voyager's transmitter may still function, but there will be nothing left to measure. And after some further point, the transmitter itself will fall silent. From Earth, there will be no dramatic event, no final transmission marked as final. The signal will simply fade below the threshold of detection. The last data point will be logged, and then there will be no more. Silence does not stop Voyager. She continues at roughly 17 kilometers per second, not fast by cosmological standards. Light travels nearly 18,000 times faster, but persistent, relentless. In the absence of friction, nothing slows her. She will not decelerate. She will not drift sideways. She will follow the path that gravity and momentum have written for her since 1977, a path that now carries her through the space between stars indefinitely. In approximately 40,000 years, Voyager 1 will pass relatively close to a star called Gliese 445, a small red dwarf in the constellation Camelopardalis. Close, by interstellar standards, means roughly 1.7 light years. She will not enter that star's solar system. She will not slow down. She will pass through the outer fringes of its gravitational reach and continue on her way, unaware of the encounter in any meaningful sense. By this time, the human civilization that built her may or may not exist. Languages have died and been replaced in far shorter spans of time. The names of the engineers printed in mission records will be as obscure as the names of craftsmen who shaped stones in ancient Egypt. The concept of NASA, the United States, and perhaps even the concept of nation-states themselves may belong to a historical era that no living mind can directly remember. Voyager carries none of this weight. She does not age the way living things age. She does not forget, because she never knew. She is a machine traveling through emptiness, and she will do so whether observed or not. The Milky Way is not a permanent structure. For billions of years, the Andromeda Galaxy has been moving toward our own. It is the largest object in the local group of galaxies, a spiral of hundreds of billions of stars, and its gravitational pull has been curving its path in our direction for as long as the solar system has existed. In roughly 4 to 5 billion years, the two galaxies will begin to interact. The encounter will not be a collision in any conventional sense. Galaxies are mostly empty space, and the stars within them are so widely separated that individual stars rarely strike each other directly. What happens instead is a gravitational reshaping. Stars are pulled from their original orbits and flung into new ones. The structured spiral arms of both galaxies dissolve and mix. Over hundreds of millions of years, the two systems merge into a single, larger elliptical structure, a galaxy that astronomers have already named Milkomeda. Voyager 1 will be somewhere inside this process, impossible to locate with precision across such timescales. A speck of aluminum and gold moving through a galaxy in the process of becoming something else. The merger does not touch her. She passes through it as she passes through everything, without notice, without reaction, carrying her golden record through a universe that is slowly but certainly becoming unrecognizable. The stars are not permanent. Every star is running down. The most massive ones exhaust themselves in millions of years, ending in supernovae and collapsing into neutron stars or black holes. Medium stars like our Sun live for billions of years before swelling into red giants and then cooling into white dwarf remnants. The smaller stars, red dwarfs, dim and frugal with their fuel, burn for trillions of years, but they too run out. In roughly 10 trillion years, the era of star formation will be ending. The raw material for new stars, hydrogen gas collapsing under its own gravity, will have been largely consumed or dispersed. The galaxies that once blazed with light will grow sparse and dark. The universe will not be empty, but it will be quiet, populated by remnants, white dwarfs cooling toward invisibility, neutron stars spinning in the dark, black holes growing slowly by accretion. Voyager 1, if the material she is made of has survived, will be older than nearly every active star that ever existed. She will be crossing a universe that no longer resembles the one she was launched into. No bright stars to navigate by. No solar wind to mark the boundary of any habitable system. Just the long, cold expansion of space, carrying everything farther from everything else. Physics, at its deepest levels, may not allow anything to last forever. One theoretical possibility, not confirmed, but permitted by certain models, is that protons, the particles at the heart of every atomic nucleus, are not perfectly stable. Over timescales so large, they make the current age of the universe seem instantaneous. Ordinary matter might slowly dissolve. Protons would decay into lighter particles. Atoms would cease to exist. The aluminum frame of Voyager, the copper disc plated in gold, the silicon of her circuits, all of it would over incomprehensible spans of time simply come apart into radiation and the lightest possible remnants of matter. If this happens, Voyager 1 will not be destroyed in any dramatic sense. she will fade, particle by particle, over timescales that have no human analogy. She will dissolve into the expanding dark. And yet, what she carried, or what she represents, does not require her physical survival. The record she carries is a copy. What it contains has already been transmitted across the solar system in signals that have been received and archived and studied and shared. The knowledge that she existed is encoded in more durable materials than copper and gold. The minds of people who read about her, who built things inspired by her, who looked up at the sky and decided that reaching outward was worth the effort. Voyager 1 was never just a spacecraft. She was the decision to try. The decision that even without certainty of success, without any expectation of return, without any guarantee that the message she carries will ever be found, the attempt itself was worth making. She reached beyond every planet. She crossed the boundary of the solar system. She entered the space between stars, a region that existed for all of human history as nothing more than a concept. And she sent data home until she had nothing left to send. She will drift long after the last signal fades, long after the civilization that launched her has transformed beyond recognition, long after the star she was born under has cooled and gone dark, long after the galaxy she crossed has merged and settled into something ancient and quiet. Somewhere in the dark, she is still moving. She always will be.